This video is sponsored by PCBWAY.
Hey there, this is Seth Schaefer from Team Jessica's Robotics, and in today's video I want to go over the design of my newest bot, Division version 4, in great detail. I want to talk about the flywheel system, how I've designed it, how I did the math to figure out exactly how fast I needed the flywheel to spin and how heavy it would need to be, etc. And just generally talk through my design approach when trying to come up with a new idea like this, which is something that so few people have really attempted before, trying to do A, hub motors, which are generally pretty hard to do, and B, a counter-gyro flywheel, which is an extra added complication that very, very few people have attempted at this scale. Now, before we dive into the design for Division V4, I'd like to take a look back at past versions of Division. So here I'm showing a highlight reel of Division version 2, various iterations on that design. You'll notice probably the key thing about version 2 is that it really likes bouncing absolutely everywhere all of the time. It does not spend that much time actually on its wheels, but rather it kind of just like constantly hits the floor with the weapon all the time. That's because the weapon sticks out on the front, the back, and top of the robot. So every time that it bounces off the floor, there's a 3/4 chance that it's just going to hit the floor with the weapon again and again and again and again. Division version 3 was a little bit better in this regard, but it still definitely had a tendency towards bouncing all over the place, especially after landing a hit. And this is in large part due to the fact that the weapon is so big with the 7.5 inch diameter that whenever I landed a hit on somebody, the hit was at like this angle. So this pushed my robot backwards more than it pushed my robot down, planting it firmly into the floor, like would be the case for the vast majority of vertical spinners with a small diameter when they hit their opponents. So here's a good fight to illustrate how Division version 3 was kind of handling. This was my fight against Mixtape at the Open Sauce event. You can check out the video, link down in the description. But yeah, basically against opponents like Mixtape, which is kind of basically a control bot, though of course they have the flamethrower, having the gyro and having the robot bouncing all over the place were a huge detriment because it made it really, really hard to follow up on the few attacks I could land. It also made it really, really hard to land attacks in the first place because every time I turn, the robot has to turn kind of slowly and the wheels are lifting off the ground, which makes me open to getting forks under me. And it just generally is incredibly, incredibly hard to drive Division version 3. It's easier than driving Division version 2, mind you, but still quite challenging. And there's so much I have to have going on in my head to be able to drive the bot because I have to manage the weapon speed all the time. I'm trading off weapon speed with steering speed, and that means I'm trading off basically hitting potential with steering speed. And that's no fun. I want to be able to kind of go balls out all the time. So having a counter-gyro flywheel would in theory help solve that problem. The way that the bot is designed with version 4 being basically invertible as well also means that I don't have to worry so much about the chaotic bouncing. It definitely can still happen, but now, like, I would say 3/4 of the time that the bot lands on the ground, it's going to be either right side up or upside down, whereas previously the back or the top or the front, the weapon would hit the floor and the bot would be bouncing all over the place. I'll start by showing you the actual physical robot, then I'll dive into the CAD design and a bit of the math behind flywheel stuff. So, starting with Division version 4, how it looks now, the design was meant to be basically as serviceable and cheap to repair as possible. So all of the parts that need to be replaced frequently are either carbon fiber that I can get pretty cheap from CNC Madness, or 3D printed TPU I can print at home, or these UHMW Uprights, which on the whole of it are a lot less expensive than CNC machined parts like I had in the last robot, or even aluminum. Laser cutting is a little bit cheaper maybe if it's two-dimensional, but this allows me to get pocketed parts. So for example, this is what the inside of one of the uprights actually looks like. It's not just a flat two-dimensional piece. And I could do that through CNC Madness for relatively cheaply. I got 3 sets of uprights and all the carbon fiber parts for 3 robots for less than $160, including shipping, which is, I think, pretty competitively priced. So yeah, there are a few different front attachments. This is missing them, but I've got a fork set up. And then On this bot, I've got a wedge setup, which is just some unhardened 4130 steel laser cut and bent by Sencut Send, because I was too lazy and cheap to deal with the titanium and didn't want to have to bend it myself because they don't offer titanium bending. And then I have a top armor config, which actually is a titanium plate that's just bolted on here because that needed to be nice and lightweight, but that just protects the battery. So yeah. The two bots with and without the flywheel, there are a few different differences. Number one, the flywheel one, instead of having an aluminum clamp ring that screws on with screws that are included with the hub motor if you buy it, I have longer M4 screws and then a 3D printed TPU friction disc that drives the flywheel, as you can see here. And then there's a polycarbonate blend spacer. I just needed something that was rigid and wouldn't like melt or deform. On the non-flywheel bot, this is what the hub motor would look like out of the box if you buy it. And it comes with 6 M4 screws and a clamping plate that's made out of aluminum that will just kind of clamp your weapon on there. So this is like the standard hub motor vert setup, basically. Now I have these aluminum plates on either side because UHMW is kind of soft. I didn't want the screw heads to just kind of pull through the plastic, so these kind of act as like big washers, basically to distribute the pressure of the screws across a larger surface area of the plastic. And I also didn't have to worry about the plastic softening from the heat and that being an issue. I don't think that the hub motor really got that hot, so it ended up not being much of a problem to worry about. But with an experimental system like this, you never really know. Probably the most annoying part of this design is dealing with the wiring. So I'll show this a bit better when I'm looking at the CAD view, but basically the hub motor has wires that come out of it. They go down the inside of this channel, and then they go into this orange printed piece, which is at the back, which basically, that orange piece both protects those wires and also acts as a way to channel the wires from one half of the robot to the other. And it kind of stiffens up the chassis. So the uprights are bolted to that orange piece, this orange piece here on either side, and to the hub motor on either side. So that makes the setup really, really nice and stiff. And then, of course, I also have the back carbon fiber support. Adds a little bit of extra stiffness too, but you can see it got cut through here, and it's still, you know, pretty hard for you to bend the sides in. The drive motors are kind of housed inside of this TPU body. Gearboxes, despite having gone through a few fights, this one sounds a little bit less happy, but this one sounds perfectly fine. On the other bot, even though the wheels took direct hits, these seem to be perfectly fine. I'll have to see if there's any damage internally later, but right now I'm not doing a full teardown, just showing you kind of the design cues of the whole thing. The wheels also, so the wheels are TPU 3D printed hubs and then a cast urethane tire. I have a whole video tutorial showing how to do that process. You can find that link, hopefully it'll be a card here, I think. I have my flange hubs, which you can buy on justcauserobotics.com, that the TPU hub bolts onto, and then those set screw clamp to the drive motor shafts. So let's talk a little bit about the gyro. Why exactly do I want a counter-gyro? Basically, when the robot is turning, because the weapon is spinning in a vertical plane, it acts like a gyroscope. So, weapon is spinning, and objects have inertia. This is, according to Newton's laws of motion, inertia is the tendency of an object that is moving to keep moving, and an object that is not in motion to stay not in motion, basically. So the tendency of an object that is in motion to stay in motion is inertia, and that works both in the linear sense and in a rotational sense. Now, in a linear sense, basically when the bot is moving, an outside force has to act on it to make it stop. This is, how Newton's laws work. That is what inertia is. In a spinning sense, though, it gets a little bit more complicated. Rotational inertia is defined basically in the direction the thing is spinning by a right-hand rule. So, in other words, you can imagine there's a vector pointing the way that my thumb is pointing when I curl my fingers in the direction the weapon is spinning. That vector is pointing horizontally, basically through the axis of the spinning motion. Now, rotating like this doesn't change the rotational momentum vector at all, which is why the robot will happily do cartwheels and somersaults, but it doesn't like it when you change that vector by actually rotating the body of the robot in the horizontal plane, in other words, steering. And so instead, you basically end up with a counter torque that tries to lift the robot up like this whenever you are turning while a vertical spinner is spinning. Now, in a lot of cases with smaller weapons or weapons spinning slower or both, that torque isn't that big, and all that you do is see a bit of pressure reduction on the outside wheel in the turn, and you don't see the whole robot lift off the ground. But Division has a huge weapon with a huge amount of inertia, so it really likes to lift its wheels off the ground when turning, like you can see in this clip here. So in order to counteract that gyroscopic force, I would either need to make the weapon a lot smaller, make it spin a lot slower, both of which would mean that I can't do that much damage and would really kind of remove all remnants of Division DNA. Or, of course, I can add another weapon spinning backwards to basically act to counter the direction of the first moment of inertia with another moment of inertia. And this allows me to lessen the effective gyroscopic forces acting on the robot. So that's what I did by adding this flywheel. Now, originally I was going to show a big spreadsheet with all the calculations I did and all the math. Honestly, I don't think anyone gives a crap and all of you would click away from the video. So here's the long and short of it. When you are trying to do some calculations for a spinning combat robot weapon, there are basically like 3 numbers to keep in mind. There is the diameter of your weapon, there is the rotational speed of the weapon, which is in revolutions per minute or RPM, and then there is the moment of inertia of the weapon. This is something that's characteristic of the shape of the weapon. Basically, larger diameter, more weight on the outside means higher moment of inertia. So a really, really big diameter disc like Division has means it has a pretty high moment of inertia compared to, say, a tiny little vertical disc, or like a Peter Bar kit with its dual disc spinner where most of the weight's towards the middle. Having more weight to the outside and a larger effective diameter tends to mean a higher inertia weapon. And the higher your weapon inertia is and the faster it's spinning, the more rotational momentum that it has. Now, rotational momentum is literally the moment of inertia, or MOI, times the speed, or RPM. This is different from kinetic energy, and these should not be confused. Kinetic energy is calculated by 1/2 times the MOI times the RPM squared. So when you have a weapon spinning at 50% of its maximum speed, it has 50% of its maximum momentum, but it only has 25% of its maximum kinetic energy. This is why, with my flywheel setup on Division, the flywheel stores about 3 times as much kinetic energy as the weapon at full speed, whereas the momentum is about 60% that of the weapon in the flywheel. So, in other words, the steering counteracting gyroscopic forces are a bit less than half of what they would be without the flywheel when I add it on there. And the flywheel subsystem as a whole, with the flywheel itself, this part is about 170 grams of spinning mass. And then there's also the bearings, and I've got this thin carbon fiber nylon print I have to put on because NHRL gets mad at you for spinning things past like 300 miles an hour that are exposed. So I had to have a flywheel cover on there. Basically allow me to add about 1/2 pound to the robot and cancel out about half of the gyroscopic forces. Now I have, like I explained in my last video, I have the ability to run without the flywheel and the robot's under 3 pounds. Like in this configuration, with no flywheel on it, robot's under 3 pounds, but I have to deal with more of those gyroscopic forces. Once again, I'd love to thank PCBWAY for making the flywheel parts. Now I've got them out of the bot so you can take a closer look. So yeah, the wheel's taken a bit of a beating during fights, but still spins perfectly well, so I'll probably keep using it. Bearings are maybe a little bit less happy. I'll have to replace those, I think, because the shields like broke off of them. probably from those impacts and just being abused well past their rated RPM in testing. And got some Sharpie on the flywheel just so you could see it spinning better on camera. But otherwise, yeah, the machining surface finish is great on everything. The tolerances were perfect. Everything was made exactly how I spec'd out in the drawings. If you want to get parts machined for your next combat robot, make sure to check out PCBWAY. They'll also do custom PCB design and 3D printing for you as well. Just use the link down below and you can get $5 off of your first order. So this is what the flywheel subsystem looks like. It is 3 pieces. So you've got this knurled piece, you've got the weight, and then you've got the shaft, which is this part here. And all 3 of these pieces are made by PCBWAY in 4140 alloy steel. And then there's just 3 M4 by 15 millimeter screws to hold the weight onto the shaft. And then 2 set screws that hold the knurl onto the shaft as well. All of these parts I spec'd with like a plus or minus 1,000th tolerance on all the critical dimensions. And PCBWAY made them exactly as designed, and they all fit together perfectly except for the weighted disc because I screwed up my drawing and said the wrong hole size. That was on me. I drilled out the holes, made it fit. So yeah, let's take a look at the final rendition of the bot here. So like I said, there's 2 different front ends. I'll show the fork setup here because it's not on the physical robot to show you. And this is pretty much exactly what the robot that I showed at the beginning of this video looks like. Other than colors, of course. So, a couple things to note. One of the really irritating parts of this design is how the fork's attached to the uprights and how the wedge attaches to the uprights. I basically had to use these hex head screws so I could fit a wrench in between, because otherwise it was going to be physically impossible to install these like TPU fork mounts this way. That's a design concession I decided to make because I can't bolt to the outside of the uprights because the chassis attaches there. And I didn't want to bolt like here because that would be likely to get torn out. I really wanted this TPU part to get damaged and then be easily replaceable as a cheap part rather than the uprights, which are a lot more expensive having to be replaced. You'll also notice the way that the flywheel is like integrated into the upright is I have the right upright here. I'll isolate that. But basically, there's 2 bearings that are kind of hidden by the knurl here. Let's hide the flywheel itself. So I just have 2 of those high-speed bearings that are just pressed into the upright. I thought this would work great. Unfortunately, I forgot to provide a tolerance on my drawing to CNC Madness to make this hole undersized so that these were actually a press fit. When the parts showed up, they were a little bit oversized holes. I had to like epoxy the bearings in, and they didn't hold very well. And considering how fast this assembly has to spin, I'm not super comfortable with that, so I'll probably get the uprights remade. Also, you can see in the design they were supposed to be black, but I told CNC Madness I need the parts really fast and not to use reprocessed UHMW. Usually the reprocessed stuff is a lot weaker and crappier, and it almost always comes in black. So I think they gave me white so that they'd give me material that would actually hold up in combat rather than just to screw with me. But I will probably see if, given a longer lead time, they can get some black UHMW just to make the robots look a little bit more cohesive. Since the white, I feel like detracts a little bit from the black and orange that I was kind of going for. I think it would look a little bit nicer with this whole black and orange setup going on. Yeah. Oh yeah, another thing is the motors. So the way that the motors go into the chassis, I think, is pretty unique. I don't know if any other robot really does this way, except for maybe like Billy might. But basically, I've got the chassis has this piece that I call like the motor plate. That's a 3D printed part. So with the motor plate removed, the motors literally just kind of slide in here from the outside to inside, as I showed in the reveal video. And then they bottom out against this flange here. The gearbox bottoms out against this. So this kind of only works with the brushed motor being smaller than the gearbox. And so that meant I didn't need that much material around the gearbox. And then for wiring, I made it so that there's a big cavity where the motor goes in here. So yeah, the motor sits there. Wires from the motor have a little bit of breathing room to come out through here. And then inside of the left cavity is only two things. Number one is the battery, which takes up pretty much all of this space. And number two is weapon speed controller, which takes up the rest of this space. And then I actually do have a third thing, which is a power distribution board, which is just one of my off-the-shelf just because switch PD boards. And that mounts to the top like that. So there are two screws that go on the inside of the chassis, which I have hidden here. Boop, boop. So I just bolt, when this bottom plate's gone, it's really easy to access. Just bolt the switch PD board there. I mocked it up with this connector here, but I ended up just running pigtails to that connector so it could sit flatter against the wall here. And then I ran two long wires to an XT30 that go out here across to the other side of the robot to the right chassis. And on the right chassis is a WECA dual ESC, which you can see there. So the WECA dual ESC is powering both motors on the right side, and then the receiver is also crammed in the right side, which I don't think I modeled. So basically, the receiver connections are all on the right side, and the weapon speed controller signal wires go all the way across to the two halves, and the power wires, two power wires just to power the WECA, go over here. The WECA has a built-in BEC that powers the receiver on the right side. So it's just 5 wires, basically. There's the 4 wires. The signal and ground for the weapon speed controller, and then power and ground for the WECA are traveling between the two halves. And then the hub motor has its 3 wires just come down along the upright. And those wires come down through this slot, which is sized especially to fit an MR30 connector comfortably. So I have an MR30 connector on the hub motor that comes in through here and then curves around and gets tucked back here next to the motor and then comes up to meet the weapon speed controller connections over here somewhere. And the battery is filling all of the rest of this space. So it's a very, very tight squeeze on the left side of the chassis in the actual robot. The right side is actually pretty spacious, but with the large receiver I ended up using, it's still a little bit crammed, but the right side's much, much nicer than the left, for sure. And you can see the battery is pretty much the largest I could possibly fit without completely changing this chassis design. I might end up changing it to try and fit a larger battery for the next version. I'm not really sure if I want to commit to that or not yet, because I think my spin-up time was really limited by how much current I could pull from this battery. And it's not really as much of a capacity issue as it is a discharge rating issue. Okay, so left upright, the wires from the hub motor come out here. They go down here and then through this slot, which again, if I show the rear stringer piece, so the wires can go through here pretty easily. I don't actually have anything securing the wires back here. They're just kind of stiff. If I really wanted to, I could probably drill a couple holes and like zip tie them to the upright just to make sure that they don't flop into the weapon. But there is like a pretty significant amount of clearance between the hub motor and the weapon in this area. So the wires would have to like bend pretty far out of their way to get hit by the weapon, but it is technically possible, especially if there's too much slack in those wires that have to go through down into here and then across. So yeah, definitely it's a pretty complicated design as far as how to package everything with the flywheel and all of that, but I try to do everything in the most simple and robust way that I could think of. So that's why I have the friction drive flywheel system. That's why I have, instead of a separate motor for the flywheel, that's why I'm doing direct drive on the wheels and I have no wheel guards. That also makes it easier to self-write, of course, because self-writing is really important with a design like this that can bounce around all the time. Switch is accessible from the top, which I really like compared to the previous version where it was from the back, and also to SSP where it's on the bottom. It's not like a big deal having it on the bottom, but on the back is a little annoying because I've got like a big T-handle that's taller, than the height of the chassis, so I have to like angle it weirdly to be able to actually turn it. So having it on the top is super nice. I just need a long enough handle that it's above here, and then it's super easy to turn. Weapon lock fits through these holes, which I modeled in, so the weapon's completely locked in place if I just stick it through like that. And yeah, as far as the invertibility goes, I guess that's one little other thing to touch on. So the way I designed everything, I started with like one basic sketch that is like a profile of the whole robot to plan out geometries of everything. And this is where the shape of the uprights kind of came from. So I basically just wanted there to be a little bit of space between the weapon and the floor from just the uprights, so even if my forks get torn off, the weapon isn't like cutting through the floor. I designed based on how large my wheels are and how much kind of clearance I wanted back here, what that rounded profile at the back would be. And this is like the 24mm gearbox and how much extra material around that I wanted. And then the hub motor mounts with the geometry that is this diameter. The hub motor itself is larger, of course. But I wanted to make sure that the uprights fully enclose the portion that it would be bolted to. And then this is the 6-inch diameter for the weapon. And this is all kind of driven. The sketch kind of drives everything. So if I change something, it should update without breaking everything. So yeah, I think that covers pretty much everything I wanted to talk about, other than just talking about how I approached the hub motor design itself. So let's get into the hub motor design, I guess, a little bit. I don't want to go too deep into it because I don't want everybody to just copy me, and even if you could find a supplier, which was very hard to find a supplier that was willing to do that for me. But yeah, I don't want everyone to just copy paste my hub motor and sell it themselves. But the CAD design's freely available on GrabCAD already. So like if you really wanted to, you could. I just assume that people won't be dicks to me, so I don't usually make a huge deal about it. Like protecting my IP. I don't patent anything. It would cost too much, and it's like not worth it for how big of a market Comet Robotics is. But yeah. So the hub motor, let's take a look at that. This one, I broke the model so that I could separate out the clamp ring like I showed earlier at the beginning of this whole video. Alright, so this is a representation of what the prototype hub motors that I used on Division looked like out of the box. So you've got the clamp ring, like I said. You've got 6 M4 screws that kind of clamp the whole thing together. Big bearings, inner hub piece, all that. If I look at the section view, you got the stator, you got your central shaft, and the magnet ring is this green section through here, and your inner hubs are this blue and this green down here, and then the bearings are the orange here, clamp screws, clamp ring, etc. So this is what the production motor is going to look like. It's pretty similar. There's a few tweaks and changes. First of all, the inside, the shaft is going to be beefier, a little bit beefier because it's made out of aluminum. I had originally designed it to be steel, so this is like a 10mm steel shaft, but now it's more like a 13mm 7075 aluminum shaft, because that fits more nicely in what the real stator shape looks to be. The magnet ring and the outer hub are pretty much 100% unchanged, other than one little thing, which is these holes that the screws go through. Originally, just to make it a little bit cheaper to manufacture, I made these through holes and kind of added a little counterbore so it would look nicer. The problem with this is because this motor is spinning so fast, aerodynamic drag plays a big factor, so I wanted to get rid of those. And so on the production motors, it's actually going to be a blind hole. It just comes out to here, just so there's a nice smooth surface here and less air resistance added by having holes spinning at super high speeds. And to the same note, I also changed from button head screws that stick out to flat head screws that'll be more close to flush. Again, to reduce the aerodynamic drag produced and make it so that the motors can spin a bit more efficiently in real world speeds. And then the only other real change is these screws are 2mm longer. They went from M4x8s to M4x10s. And that they'll also come factory with blue Loctite, basically securing these two screws. These screws come not Loctited because you have to remove them to install a weapon blade, but I would strongly recommend if you buy a hub motor from me that you Loctite these in place once you've attached your weapon disc, unless you're planning on swapping weapon discs all the time. And even if you are planning on swapping all the time, use purple Loctite, which is like basically vibration resistant Loctite. That is not going to make it too hard to remove it if you decide to change weapons, but it'll prevent the screws from vibrating out while spinning. Because I had problems with that using the rubber disc version. Yeah, pretty much everything else is identical between the factory and the prototypes, and you'll be able to buy these motors from me. They should be in stock around the end of March, maybe beginning of April, because of the Chinese New Year delaying production a little bit. And also the colors are going to be different. That's the other thing. These came out a lot more red than I intended. I really wanted this to be kind of like an orange to match Division's look. So I sent them Pantone colors to use for the final production one, so it should come out to be more or less like this orange or something close to it. And I think that'll look a little bit nicer, at least in the context of Division, and it'll also differentiate it a bit more from the red JCR series motors as well. So yeah, construction of the prototypes was 6061 aluminum for the outer hub and inner hubs and the shaft, but the production motor is all 7075 aluminum, which is like 60% stronger, and it's like the exact same weight. It's just a little bit more costly. But the price of the motor should be what I said. It'll be in that, like, I think it'll be about $95 for each motor, maybe a bit less, even with the 7075 aluminum, because I decided to just buy a larger quantity to offset the cost of the material being a little bit more expensive, since I wanted this product to be as good as possible. And like I mentioned, these motors will come from factory with epoxy on the magnets. So epoxy magnets in here, and there will be epoxy on the stator as well, just to prevent the wires from vibrating loose and getting caught in the spinning motor can and wrecking anything. And I'm also, in addition to selling the entire motors, I also will be selling these outer hubs. Bloop. So this outer hub, I plan to sell separately. I ordered like 20 of these that you can buy just separately. So if, on the odd chance that you do crack a magnet, despite them being epoxied in like you can see, you can just replace this outer hub, and it'll probably cost about half as much as buying a brand new motor, because it's about half of the motor. And if you're interested also, this is what the stator looks like with just the shaft pressed into it. With the epoxy, this is how it comes from. This is how it'll come from factory. Nice, neat, and tidy package. And kind of just boop, pops in there, and then the inner hubs and the bearings press on the outside, and you end up with something that looks like this. The final motor. Now, this one is one of the prototypes. It says 1250 kV. I think the final production ones are going to be 1200 kV or so. Basically because of how heavy the outer hub is and the drag that I talked about, aerodynamic drag. They came out when I measured with the tachometer at only like 1100 kV, even though I had originally spec'd for 1250. So I asked them to increase the RPM a little bit and give me closer to a 1200 real world kV, because Division with the 1100 kV was already, you know, pretty powerful, as you'll see in the upcoming event recap. Speaking of which, make sure to subscribe to my channel and click on notifications so you don't miss it when the event recap comes out. And also, if you want to see all of Division's fights right now, if you go to my Patreon, which I'll have linked in the description, you can actually look at the Seth Cam cut of every single one of my 5 fights from the event. There are 2 that were live streamed on NHRL's Brett Zone channel, but the other 3 fights you won't find anywhere else right now, and you can check those out from my perspective on my Patreon exclusively until the event recap comes out, when I show all the footage from my standing camera and the Seth Cam and the stream all kind of wrapped together. All right, that's all I got for you today. If you have any questions, make sure to leave them down in the comments. I'm sure I didn't answer everyone's possible questions, and I'm also sure that 80% of the questions that I get in the comments will be from people who didn't watch the whole video, and I already answered the question later anyway, but that's just how YouTube do be. All right. Thanks for watching, everyone. Bye-bye.